Hello everyone, we are going to start a new chapter, and as you saw in the title, we're trying to learn about what make batteries work, and in order to do that we need to understand a type of chemical reaction that is called redox reactions. Just to set up an introduction, electricity, and in particular stored electricity in batteries, have become a critical element in a lot of portable applications that we have in phones and cars and so on. And before we can talk about what makes these things work, we need to understand sort of the fundamental chemistry associated with generating electricity. Now, first off, what we mean by electricity is just a flow of electrons. So when we have a circuit like this, which just means like it's a loop of connected path for electrons to flow, the electrons can start from one end, and remember that electrons are negatively charged, so they're attracted to the positive end or positive pole of the battery, and then they enter that and then gets repelled, and then it goes round and round like that. Now you might say, why would the electrons want to start moving around? And that's because there is a certain chemical reaction in the battery that allows that electron motion to be produced, and that's the whole point of the battery, is to generate that chemical reaction. Eventually the chemical reaction will run out, and that's when the battery dies. In order to understand how these electrons are generated, we need to dive a little deeper into something called the oxidation, reduction, or redox reaction. This is a reaction where a reactant transfers an electron or more into another reactant. So in this picture right here, you see that element A is transferring electrons to element B. Now at the beginning, both A and B are neutral. They don't have an excess or a deficit of electron. But once A transfers that electron to B, then A now has one electron deficit compared to its original state, so now it has a positive charge. And then B has an additional electron compared to its original state, so now it has a negative charge. So it becomes a cation and an anion. That process where A loses an electron is called oxidation, and the process where B gains an electron is called reduction. That's the reason why the reaction is called oxidation reduction or redox. So this is an example using actual elements and compounds, a reaction between zinc metal and copper ions, and the ions can't come in on their own. They have to come in the form of an ionic compound, so we're using copper sulfate here that's dissolved in water. Here's your zinc, here's your copper sulfate solution that's bluish, and when you leave those two things in the beaker for an extended period of time, you see this happening where the bottom part of the zinc that's exposed to the copper ion containing solution started to change its appearance and look like this over time, and that's actually copper metal that's covering the outside of the zinc now, because the reaction occurs at the surface. The other thing you can see is the intensity of that blue color changes, so that tells you this solution is a lot more dilute in the concentration of copper, because the copper ion is what gives it its blue color, but it's a lot less blue now because much of that copper ions have been converted to copper solid. So the reaction itself is written this way. Zinc becomes zinc ions. So the zinc literally just dissolves and becomes zinc ions, which float around here. You can't see it, but zinc ions have no color. That's why the solution is less blue. Copper ion, which is blue, becomes copper metal, which are all these sort of blackish type solid, and because the copper ion is the blue color ion, the color of the solution becomes less blue over time. Another way to say this is zinc is oxidized to zinc 2+, and copper 2+ is reduced to copper. As we said earlier, is that when it's oxidized, it becomes more positively charged, right? Because it's giving away electrons. And when something is reduced, it becomes less positively charged or more negatively charged. And in this case, copper goes from 2+ to neutral. That tells you that copper has gained some electrons. So here's an example of a couple of redox reaction. You should see if you can identify the species that is reduced and that's oxidized in this case. And as a reminder, the ionic compounds break apart into ions when they're dissolved in water. So something like this chromium 3 nitrate actually breaks apart into chromium 3 and nitrate ions, and the reaction is really between the aluminum metal and the chromium ion in this case, generating the aluminum ion, which again comes in the form of the compound, and chromium metal. So think about that. Think about what is oxidized and what's reduced. So the picture that I just showed you earlier, it's just a chemical reaction of zinc and copper ion. There is electron movement here, but that electron movement is not being harnessed to generate electricity. Right now, all we're having here is the electron directly being transferred from zinc to copper, and so we don't get anything except heat here. If you want to make it useful, if you want to light up a bulb, for example, you need to create a circuit, which is that path that I was talking to you about earlier that allows the electron to go around. And so that circuit is constructed just like this. So this is a picture that shows you a typical setup of a battery. So instead of putting the zinc and the copper in the same container, we separate it into two containers. And we put on one side the zinc metal, but then the zinc metal has to be able to become zinc ion. Remember, that's the whole reaction. Zinc metal becomes zinc ion. So I need to put a solution in here that have those ions so that that process of zinc becoming zinc ion can occur on this side of the compartment. On the other side of the compartment, I have copper ion, but the copper ion can't become copper metal unless I put some type of a metal that allows that electron to flow. So the electron must flow from zinc to copper, and that metal is necessary. Now that metal could be copper, as shown in this case. It could also be something else. It doesn't have to be copper. It's really the purpose of the metal is just to allow electrons to flow. So once you separate these in two compartments, you put a separator in between them, but that separator is something that allows the ions to flow back and forth. That's necessary, otherwise the charges are not going to be balanced on both sides. And if the charges are not balanced, then the flow of the electron would stop very quickly. So once you allow that to happen, then this electron can keep on moving around like that. So the electron will flow from the zinc, which is the thing that's oxidized, into the copper ion, which is the thing that's being reduced. And as the electron flows, that kinetic energy of electron movement powers this light bulb right here. So this is the actual setup. In this case, we don't have a light bulb, but we have a meter that shows you what is the actual potential difference between the two sides here. And that just measures how much electron is flowing from one side to the other. This is the zinc, this is the copper, and it's connected in two different compartments. And then there is a flow through this meter that measures quantity of electrons that's flowing, right? So it's the same idea here, and this is just showing you in practice what it looks like. So this would be what a very simple battery would look like. Now, the batteries that you buy, all the components here have been packed into a cylinder-sized container so that it becomes portable. So let me just talk a little bit about some of these components that I just described already. You need your two reactants, the oxidized reactant, which is zinc, and the reduced reactant, which is copper ion. You need these solutions, as I said earlier, and they're electrolytes, which, as you recall, are solutions that have ions in them. And the purpose is to allow the electrons to flow, because if there's no ions, then the electrons will not be able to flow, as you recall on our discussion of electrolytes. There has to be a path for the electron to flow from one side to the other, from the oxidized to the reduced side. And so we make up these paths, which consist of the following. These pieces of metal, they're called electrodes. So the side where the oxidation occurs, that electrode is called the anode. The side where the reduction occurs, that electrode is called the cathode. And then there's a wire that connects the anode with the cathode, therefore forming that whole path for the electron to flow. And then lastly, we need the ions, because once you produce a lot of ions on this side and you consume a lot of ions on this side, then there's an imbalance of charge. So we need an ion to be able to flow back and forth through the two compartments. And we use something called a salt bridge. Ions pass through that salt bridge.